Good morning and good afternoon to everybody. It's great to see all of our attendees logging in with us today. While you continue to get settled, maybe grabbing a beverage and your notepad, please take a moment to review the screen you see now. Sharing a few FYI tips to help you navigate your go-to webinar attendee control panel. My name is Nicole Freeman, Corporate Marketing Manager with Plastek Group, and I'll be here on with you today as organizer and moderator for Plastek Academy. Today's webinar with ExxonMobil Chemical Company will begin very shortly with a video message.
Hello, and welcome to the Plastek Academy. I'm Dennis Preshak, President and CEO of the Plastek Group. Thank you for joining us here today for another segment of our monthly webinar series. When our customers work with Plastek, they don't just get a molder that molds parts. They get a high-quality partner in their complete package design process that includes industrial design, product design, mold design and building, molding, value-added assembly, and, where desired, decorating. They also get a partner connected to some of the greatest companies in our industry that will keep you and your company on the leading edge. One such company is ExxonMobil Chemical Company. Exxon has been a key plastic supplier for many, many years. They have helped us solve difficult technical problems and helped us become an integral part of a reliable, high-quality, robust supply chain for our customers. Today I want to introduce you to Kevin Wielhowski and his team to present an intro to polymers and market outlook. To everyone watching, good luck and happy learning.
Hello all, I'm Kevin Wielhowski. I'm the account manager for Plastek here at ExxonMobil. I am based in Pennsylvania and I am virtually here with Jim Luce. Jim, why don't you introduce yourself?
Yeah, I'm Jim Luce with the Polypropylene Technology Group of ExxonMobil. I am located in Baytown, Texas, where our Baytown Engineering Complex exists for lab testing and reactors. That's where our reactors are located for polypropylene. And Baytown is about a half-hour east of Houston. So,
great. Thanks, Jim. Next slide, please, Nicole. As we know, today we're going to look at an overview of polypropylene. So we'll move into the agenda, please. Okay. So today we'll talk about some market economics, polypropylene types and uses, impact copolymers and making polypropylene tough, why crystallinity is so important, polypropylene physical properties, and we'll wrap up with a summary and some discussion along with some poll questions along the way. Next slide, please. So what drives polypropylene pricing? Three key factors really, but broadly it's going to be macro and microeconomic moves, broadly economic growth and trends, market-specific growth such as auto or hygiene. Secondly, feedstock pricing at the highest level, crude and natural gas, and then there's propylene pricing. Lastly, any type of supply and demand imbalances, producer capacity utilizations, outlook for capacity and demand growth, trade flows for polypropylene, propylene, and finished goods, and lastly, types of supply disruptions. Next slide, please. Here we're going to look at crude and propylene pricing. Certainly we've stabilized post-COVID, and after crude bottomed with COVID, has now recovered to near low end of the historical range. propylene inventory remains historically high. However, refinery capacity utilization may negatively affect its availability. As a result, propylene pricing has ticked up. Some recent feedstock pricing drivers have been OPEC's action around the supply cuts and related price changing. This has been balanced by PDH, or on-purpose propylene capacity utilization and reliability. And lastly, weakness in refinery capacity utilization may impact availability going forward. Next slide, please. As the US has come to grips with COVID, there's been recovering North American polypropylene demand, and supply shortages have led to an inventory drop and price pressure. Polypropylene continues its strong recovery, with auto and essentials leading the way. Month on month, August domestic demand was off about 2%. However, demand in the June through August period was the highest 3-month period in the last 13 months. Year-to-date demand is off about 2%. August producer capacity utilization, or CU, was around 86%, while IHS, the consultant to the chemicals industry, suggests effective polypropylene capacity utilization was much higher in the 93 to 94% range. Year-to-date capacity utilization is lagging 2019 at 85% and lagging 2018 as well, where we had about 90%. In August, domestic producer inventory dropped about 2 days to 29 days demand inventory, which was a 3-year low, much below 2019 at 37.5 days and 2018 at 33 days. August converter inventory, excluding imports, is around 13.5 days demand inventory, slightly larger than both 2019 and 2018 at around 8 days each. Exports declined from 37 to 23 KT from July to August, after July saw the highest level since January of 2017. August imports are flat versus July, and year-to-date down about 38%. Increased imports are not expected to be seen in the domestic market until the November-December time period. Next slide, please. Here we're going to look at North American propylene and polypropylene pricing and metrics over a multi-month period. First, we'll start with propylene. Propylene inventory has gone from balanced to tight to more balanced from the August through October period. Motor gas demand has been challenged, which will impact demand availability. Capacity utilization has been high. And again, IHS has noted pricing in the August-September period around 36 cents a pound. That was 3.5 cents higher than July. Moving on to polypropylene. Inventory was balanced to tight in the August period and has gotten progressively tighter in the September and October periods. That is driven by strong polypropylene demand paired with polypropylene outages, predominantly resulting from Hurricane Laura. Capacity utilization has been balanced to tight and getting tighter. Again, as a result of Hurricane Laura, for a 2-day period, roughly 50% of capacity was offline. LyondellBasell's Lake Charles facility is expected to restart sometime here in October. Demand was recovering in the second and early third quarter and has gotten progressively stronger, again, led by essentials, hygiene, personal protective equipment, and auto. There's been multiple supply impacts through this period of time, and there are currently multiple force majeures outstanding. As a result, the industry saw a 3-cent polypropylene margin move here in September. Last month in September. Lastly, regarding trade flows, there is no arbitrage opportunity from Europe or Asia Pacific to the US. Next slide, please. So to wrap up my portion of the presentation, we'll have a poll question. What drives polypropylene pricing? Is it the macro and micro economy? Is it feedstock pricing? Is it supply and demand imbalances, or is it all the above? A couple moments for you to answer. Well, there you go. The vast majority got it correct at 92%. Certainly all three of these items do influence polypropylene pricing. Again, macro and microeconomic movements, feedstock pricing such as propylene, and then supply and demand balances. Again, all impact polypropylene pricing. Next, I'll turn it over to Jim. Thanks, Jim.
Okay, I will address the polypropylene portion of the presentation. This presentation is a brief overview, really designed to be like a basic PP 101 approach. It really is designed to offer the knowledge base necessary for suppliers such as yourself and other folks to supply into the injection molding market segment of the business. So I'll start off with what PP is. PP is a polymerized resin that derived from the monomer propylene, and it makes a long polymer chain that is well suited for many types of processes, but it really is a widely used product in the injection molding segment. Two types of catalysts are predominant. There are many types of catalysts, but the very well-known commercialized catalyst is the Ziegler-Natta catalyst. Many commercialized products use this catalyst because of its high yield of reaction, and it offers a well-blended product, meaning the molecular weight distribution is fairly broad. It lends itself well to blending and coloring and offers the property base necessary for most applications. In contrary, there is a metallocene-based catalyst system that ExxonMobil offers. That catalyst offers different structure, typically a narrower molecular weight. The properties are a little bit more specific, and it's a cleaner process typically used in food packaging, healthcare, and medical applications. So with that being said, that's kind of the base approach to polypropylene. There are three different types of polypropylene widely used, and these grades or categories are random copolymers. If you look in the picture there, you can see on the far left is a random copolymer type food container. It's shown in the microwave because polypropylene offers very good heat resistance, and randoms are clear, so the content is important. You can see what's in there. If we look in the middle slide where we see caps, it depicts a homopolymer and the strength that a homopolymer offers. In particular, if the container is for carbonized beverages, that strength to weight ratio is extremely important for securing those lids to those types of containers. And then the more complex type of polypropylene is called an impact copolymer, and that offers that high level of stiffness necessary, but also greatly improves the degree of toughness for applications requiring very harsh environment abuse. A pallet is one of those. So in general, do one click there, Nicole. Polypropylene are very versatile. They're low density of a 0.90. The density doesn't change between all three types of these polypropylenes, and it is all based on a high stiffness base resin polymer being the polypropylene backbone of that resin. If we look at this picture here, we can see these resins in their natural form, and it can quickly remind us who work in plastics all the time but may not see the natural state, that you can quickly identify the three different types of polypropylenes. The random on the left is clear. I'll note that these plaques are thick at about 100 thousandths thickness, and what you can see through it, has good clarity and good contact clarity. You can see the wood grain through that plaque, and that plaque's on the left. So the plaque in the middle is a homopolymer. There's just a little bit of contact clarity you can pick up through there, but it's a grayish off-white. And then ultimately the ICP is milky white or completely opaque. The refractive index of light going through there is totally blocked by the monomer that is within that ICP. So that gives a natural, when we refer to natural resins, that's what they look like. In the next slide, I'll touch on what is the foundation of polypropylene and why it's so value add or valuable to, in particular, the injection molding market. There's, again, the three different types: the homo, the random, and the impact copolymer. I mentioned the Ziegler-Natta catalyst system earlier, and different catalyst systems have different melting points, but at least in this case, I'm showing a 162 to 165 degrees C melting point. That is the key to stiffness. The higher the melting point, usually the higher the stiffness, and it has fast cycle time and good heat resistance. One of the very important design features of polypropylene is that it can offer living hinge capabilities if properly designed. Caps and closures can have the snap feature, and a great benefit to taking what would traditionally be a two-component assembly. Now you mold it all in one design, and it saves time, money, and convenience to the end user. In talking about the foundation of really the heat aspect, the high heat resistance, if we look up into the chart, we see the gray bar, which represents homopolymer, and it tends to be up to the higher stiffness end of the flex modulus, but it tends to be brittle. So the beauty of polypropylene is then you can take that homopolymer that may be deficient for some applications and toughen it up by adding some modifier, in this case an EPR rubber, and change that level of ductility response. You're also changing the flex modulus, so the flex modulus is going to move accordingly. But the heat resistance stays the same because that polypropylene matrix is spread throughout. That what is ultimately what controls when the resin will melt. So in contrary to that, the random copolymer, where the ethylene is inserted at random intervals throughout the polymer chain in more or less a solution stage, that can offer benefits of improving the ductility of the random copolymer. At a very low level, say below 4%, you can still maintain some good clarity of random copolymers. But if you add too much ethylene modifier, you end up losing that flexibility. The RCP goes from being very rigid to very flexible, and certainly the haze aspects, it gets hazier and hazier with the amount of ethylene added. Ethylene is referred to as C2 here. So ExxonMobil offers many different types of polypropylene grades. In the random copolymer area, our specialized grade, one of our big workhorse grades, is PP9074 MED. Especially suited for medical applications as well as other applications of food packaging and healthcare. This is a very rigid polypropylene, and in contrary, we offer very flexible RCPs with much higher levels of ethylene. And when we get into that category of elastic type products. That's called our Vistamax series of products. So the last type of homopolymer is the impact copolymer. It is the most complex and usually is designed to meet very specific requirements within applications and underscores the need for toughness. In our next slide, I go into detail about what makes up that complexity of an impact copolymer. Initially, when homopolymers were first introduced in the 1950s, they quickly realized that relatively brittle homopolymer could have much broader uses if it could be tailored. And in that time frame, they would mechanically blend modifiers in. And since then, in the early 1980s, like 1982, they first came up with reactor grade ICPs, which are typically made in a series of polymerization reactors or in situ, one right after another. And that's what ExxonMobil produces today in many locations, our Baytown facility and our Singapore facility. These impact copolymers start off by making a homopolymer that is designed for additional blending. If we look in the picture here on the left side, we see pictures of actual granules. These granules are small, certainly less than 1/16 of an inch. They might look like granulized sugar or coarse sugar or perhaps powdered laundry detergent, that type of granule. And when they're specially designed for the incorporation of ethylene to make an ICP, those granules are porous in nature. And so when the homopolymer is made, typically in loop reactors, and then gets fed on to the reactor that's in series, being that gas phase reactor, the ethylene is incorporated and infused into the porosity of that granule, and that finally makes, the final result is the ICP matrix or morphology shown on the right side of that picture. The rubber domain, the EPR, is the dark spots. The homopolymer is the white area that's continuous through that phase. And the rubber domain is what allows the energy to be absorbed. And depending on the size and frequency of those domains can offer that tailored property performance for whatever degree of toughness you might be looking for just a touch of toughness or a product that's all the way completely a no-break status in terms of IZOD and offering like 320 inch-pounds or greater of blunt force, like Gardner impact results. So the pictures or the granules are shown here, but ultimately when you get to the EPR infused granule, then it has to go through the finishing step of the final extruder at the base of the reactor, and you pelletize that product to the typical pellets that we know today, maybe 1/nth type cylinder shaped pellets. One other aspect to making homopolymers in general, all types of homopolymers, with a base resin, is that the molecular weight of those resins dictate how that material will flow. And we know in the injection molding market, flowability is very important. The typical range for injection molding products is from a 4 MFR flow rate all the way up to 100, maybe a little bit over 100 MFR. And that, a low melt flow or high viscosity resin flows really slow and oozes at melt temperature. And when you're into 100 melt flow, it's going to flow and flow. It's considerably easier. All this is important for the injection molding process. If a resin flows too viscously or resists flow, like a 2 melt or below, or even a fractional melt flow product, the pressure generated in the injection phase of the machine is just too great and narrows that processing window considerably. On the flip side, Exxon makes very, very high flow resins that flow like hot water, so to speak. And those are used in the non-wovens industry for textile, like medical gowns and things like that. And in some cases, 500, 1,000, even 1,200 melt flow ranges. So a wide diversity of molecular weight base resins are made in many different ways and using different catalyst systems alike. So in the next next slide, I'll talk about fundamentals of polypropylene and basically talk in detail about nucleating agents. And a nucleating agent to a reactor polypropylene or a neat resin is an additive. And before I dive into nucleating agents, I'll talk more about other additives. Neat resins directly from a resin supplier, we can add many different additives that help improve the resin in multiple stages, either in the processing stage, it being our process or the customer's process of injection molding, or that benefit the actual end use application. Those types of additives can be slip agents or anti-statics, clarifiers, UV stabilizers, and in general, all polypropylenes have some degree of base stabilization or thermal stabilization, and that is addressed with primary and secondary thermal stabilizers. Primary being the stabilizer that protects it through our process and the customer's process, and pretty much is used up by that point in time. But then there's secondary thermal stabilizers that help protect in the finished product. An example would be a part requiring long-term heat aging properties for under hood applications in a car, or containers that are exposed to high temperature that prevent the breakdown of that polypropylene. So about nucleators. Nucleating agents, there's different types of nucleating agents. Some are more powerful than others, but the end result is that a nucleator will change the crystallinity of the polypropylene, and when that crystallinity changes, you're improving different aspects of that polymer structure. You're going to offer higher heat resistance, you're going to offer higher stiffness, higher tensile properties. There's other properties that go hand in hand that could be considered like the hardness, the surface hardness of the resin. Very beneficial. And in an ICP, the beauty is that those nucleating agents will not affect or have very, very little effect on the actual impact properties. Where they do have a significant effect is in the dimensional shrinkage or warpage of the part. And these dimensional aspects can be influenced by how the material is molded and how the shape or geometry of the finished part. And then ultimately, the biggest benefit to an injection molder is it can improve the cycle time and make for more efficient operations. If we look at the diagram here, essentially a nucleator is shifting that T sub C value by as much as 20 degrees, and that baseline without nucleation T sub C, it can change depending on the type of catalyst systems used, but essentially you're getting a 20-degree offset or improvement in T sub C values. How these products are, or how the effects of nucleators are measured in a polypropylene, use a DSC machine, and we look at the crystallization temperature, again T sub C, and then we can also look at the rate of crystallization, which is called T1 half time, or isotherms is another name that they are called. In the next slide, I'll give specific examples of how this can improve and offer flexibility to the injection molding market or segment. So again, the benefit is that a resin supplier can offer a grade either nucleated or non-nucleated and offer this flexibility. If we look at the chart and look at the blue bar, that represents a nucleated metallocene homopolymer. And I'll just make one comment about the metallocene here. The metallocene, again, is a very narrow molecular weight and offers, in general, lower melting points. And so everything is shifted lower on that scale relative to a Ziegler-Natta type catalyst system, again, which has a melting point of about 165, where in this case, this metallocene grade has a melting point of about 158. So it's shifted lower in general. So that's one benefit, one distinction that can be made here with the nucleating agent is that metallocene may need that improvement. Think about this graph from a molten standpoint or from the resin's point of view. The resin is molten in the barrel of the machine. It's being injected into the cavity. At that molten state, the resin is about 230 degrees C or 450 degree F. And as soon as it's injected and hits the sidewalls of the mold, it begins to cool. And once the cavity is pressurized, the heat transfer out of that resin is very, very rapid. And that's why this chart is shown in terms of this is the T1 half-time or isotherm representation of these materials. So what happens is that resin is cooling rapidly. Once it reaches its T sub C value, in this case with a nucleated resin, that temperature is 121 degrees C. It's going to solidify or crystallize. And once that kicks off, it's very rapid. So the isotherm representation of this nucleated grade is about 0.35 minutes. With the exact same conditions to the non-nucleated grade, it's 5.3 minutes. So it gives us an indicator that we are really influencing the thermal properties of this resin. And the biggest benefit is cycle time efficiency improvement with the nucleated resin. But pros and cons is the key thing here, in that not always does a nucleated resin help your injection molded application. If the flow properties are such that areas of a part will cease to flow, meaning they've reached the end of their flow destination, and other areas within the cavity are still flowing, that's going to be offset cooling. Once a resin ceases to flow, it has nothing else to do but cool and solidify. When that occurs, it can lead to that warpage and dimensional delta that I talked about, and that could be detrimental to the actual application in terms of warpage. So there's benefits to having a non-nucleated grade. That basically means you're going to get a wider processing window at the expense of maybe efficiency and time of and cycle time. So basically, nucleated grade speeds up that cooling time and rapidly improves the cycle time. In general, this offers a high degree of versatility to the resins, and again, it offers grades that are nucleated, non-nucleated, gives the injection molder choices to solve what could be very difficult problems. In the next slide, I'll give you an example of how grade recommendations are made. What I show here is that we have in the yellow triangle totes or storage bins that somebody's asking for a grade recommendation for, and ultimately the mindset of myself or a molding engineer at our customer would be what's important. And what's important in this case is the stiffness, which is typically measured by flex modulus or the tensile, the HDT or hardness values. They all go hand in hand, correlate in the same direction, versus the degree of impact strength, which is measured by the the IZOD impact, which is a notch sensitive type method of impacting, and then Gardner impact, which is blunt force. Both hand in hand can give you good feedback. If you're looking at one versus the other, it can be a little bit tricky. And the reason that can be tricky is because in the world of polypropylenes, that polypropylene being a semi-crystalline resin, meaning it's mostly crystalline, but there is some degree of amorphous content there, and that can be a little bit misleading sometimes in IZOD impact testing. When I get posed with a question like this, which grade is best, I recognize that totes are relatively large applications. They might have thinner walls, or certainly a producer of totes would be conscientious of that. And so I would start off by offering an ICP that's a 50 melt flow rate. The base componentry of that ICP would be to have good color stability, knowing that the parts are typically colored and have fast cycle times. The grade I pick is PP7505 KNE3, and that again is an ICP. On the green bar there, the balancing act again is stiffness to impact. And this is a level green bar, meaning it's well balanced. The stiffness can add to the stack height ability if you're stacking 4 or 5 totes high. And then if you're concerned about the stack falling over, you don't want a disappointed customer with a bunch of broken parts. So drop resistance or drop impact is important. This is very recognizable to most of us when we have gone into stores to pick, even look at storage bins. The random copolymer offers that clarity, but can't get close to this level of impact resistance that an ICP has. And usually when you look at a stack of totes, you'll see cracks at the bottom edges of those random copolymer totes. Nicole, if you give one more click there. So we see the end use of these totes, and that it really exemplifies a satisfied customer or a satisfied application designed to meet the wide variety there with those orange totes. So we have a technical polling question that comes up next, and this question is as follows. I'll give you a few seconds to look at that. The question relates to, if you can see it there, that what is beneficial to a nucleating agent. So the answer is all of the above. And I have a hard time seeing all the results here because I'm on a phone, but most people, 74% of the people got that question right. So that concludes my technical portion. The next slide we go into is our summary and discussion slide, and Kevin will address these questions.
Thanks for your insights, Jim. Appreciate your time. Okay, so polypropylene pricing is linked by a diverse economic drivers, and according to IHS is expected to remain at historically affordable levels. Polypropylene is a versatile semi-crystalline thermoplastic used in a wide variety of applications from injection molding to extrusion. Polypropylene grades are frequently selected based upon melt flow ratio so that processing parameters remain similar. Physical property optimizing for application functionality requires balancing stiffness and toughness. And lastly, additives can be added to the PP grade or added at the press to color or regrind needs. Now we'll take some questions.
All right, thanks guys. We have just heard about the market outlook and intro to polymers. So on behalf of everyone watching and listening today, and from us all here at the Plastek Group and the Plastek Academy, I want to give a big thank you to ExxonMobil Chemical Company and our guest speakers today. Kevin and Jim, thank you for your time and expert knowledge.
Thanks for having us, Nicole.
Now for a shout out to our audience. Before we conclude today, as you can see on the screen right now, please take a few moments to share with us. Submit your questions on today's topic and using the question text box on your control panel. All you have to do is type it in and hit send. While you're writing in, I also want to remind everyone, we have provided 2 handouts you can download for your reference for later on. But be sure to check them out and open them before you leave here today. While we collect your questions with the time we have left, Kevin and Jim are here to answer a couple frequently asked questions about the materials they shared with us today. So for starters, Kevin and Jim, we know that 3D printing has become pretty popular in the plastics industry. We get asked a lot, can polypropylene be used for 3D printing?
Yeah, so Jim here, I'll answer that question. Yes, polypropylene can be used for 3D printing. As I mentioned in my presentation, polypropylenes are semi-crystalline resins, so they may have their sweet spot or advantages for a 3D printing. But with that being said, the degree of having a very dimensionally stable or specific type of 3D application printed out may be challenged with that semi-crystalline resin, but certainly it can work.
Okay, thanks, Jim. I do see some questions coming in, so I'm just going to take a moment to read through those and see which ones we can answer for the audience today. It looks like they'd like to go back to addressing the nucleating agents. Have a couple about recycling. So let's see. Do you find that nucleated resins have any determining factor on recycling potential for the material?
So in general, a nucleated product will maintain that level of crystallinity or the effect of being nucleated throughout several heat cycles. So the benefit of the nucleator will not be lost in recycling. And other than that, I mean, there's no real pros or cons. It can certainly go in the improvement route of offering maintained stiffness or maintaining those property integrity that you're looking for by having a nucleator in there. I'm not sure if I answered your question specifically or not, but in general, that's what nucleators offer for regrind or recycle.
Okay, great. Thanks, Jim. And we can get back in more detail with the audience as well later. I think we'll have time for about 2 more questions. We're going to bounce over to Kevin, perhaps. Let's see. What is the real or effect or impact of Hurricane Laura on supply of PP and pricing? Is that something we can answer today, Kevin?
Probably not very full, but as I noted in the slide, Hurricane Laura for a period of time took out about 50% of capacity. I think one of the assets were down for an extended period of time. Certainly we've seen tightness in the market as a result of that, again, diminished supply. When you couple that with a period of relatively strong demand, price balances. So, and if there's a more detailed question around that or longer term, you can submit it to Nicole and we'll try to get back. But that's our view around the implications of Hurricane Laura.
Okay, great. Thanks, Kevin. Okay, one more. The time we have left. We'll take another question on the material side of things. The question is, how does the choice of color influence polymer properties, both for manufacture and for end use?
Repeat that question. There's some static in the background. Nicole?
Sure. The question is, how does the choice of color influence polymer property, both for manufacture and for end use?
Oh, okay. Well, colorants can have several different types of influence on the molded product. Depending on the type of colorant pigment used, that the pigment, like blues in particular, can lead towards nucleated response. The pigment particle size can influence how the finished molded product basically creates crystal structure. The colors themselves, because depending on the letdown ratio and that makeup or composition of the colorant, could slightly dilute the physical properties of the base resin, but usually that's not of concern. An application is usually wide spectrum enough not to be affected by that. And other than that, I can't, there's some aspects, and actually this was one that I experienced with Plastek, is sometimes the different colorants can affect the surface coefficient of friction and lead towards different touch or feel aspects. And in some cases, in high-speed assembly lines, that is noticed as a bit of a hiccup or a drag on the conveyance process. So those are some of the things that I've experienced.
Thanks for your input, Jim. Okay, everyone, I'm looking at the clock and we want to be conscious of your time and certainly appreciative of your time with us today. So we're going to go ahead and collect the rest of your questions and, however, complete the webinar at this time. So please note that our Plastek Academy team and sponsors will review your questions that you wrote in today and that we weren't able to get into or answer in full detail. So we will either do that at the end of our wrap-up webinar event, at the end of our Plastek Academy series schedule, or get back to you individually. So from all of us here today and everyone at Plastek Academy, the Plastek Group, and today's sponsor, ExxonMobil Chemical Company, we again thank you for attending and actively participating in our Intro to Polymers and Market Outlook event. As you exit the webinar, you will see a brief survey. We appreciate your time, your feedback, and we look forward to bringing you more great topics in our Plastek Academy. See what the next series topic is at plastekgroup.com. And until next time, have a great day. Thank you.